Up until now, on all the work we've done with our limits, you have been given a specific function. Typically, it's been a linear function. And you've been given the value that x is approaching, and you have been given the actual value that it's equal to. And what you've been asked to do so far is, given all of that information, verify that it is in fact correct. Verify that that number, that limit, actually is the correct value. You have been given something like this. Given the limit, say, as x approaches, let's say 4 of 3x minus 1, you've been given that that is equal to a specific number. I've given you this number. And then you've been asked to verify that this actually is correct. What we're now going to do is something like this. Suppose you're given some more elaborate unknown function. And the question is, if you're given some more elaborate function, as x approaches 4 for this function, what then is the limit value? What does that mean? How do we use that? How do we use that as a tool to find more information that we'll be dealing with in our calculus work? And so that's what we're after now, is given a specific function, we want to be able to evaluate that limit. Now, to do that, we need to have some specific, it turns out, one way to find the limit is to simply guess. If you're given limit as x approaches 2 of x to the 4th minus 6x plus 7, you could just guess a number, 18. I have no idea if that's correct. I'm going to guess 18. And then you could do a delta epsilon proof. And if it worked, then yes, 18 is correct. If it doesn't work, guess again. Well, it turns out guessing is not a particularly efficient way to find the limit. It turns out there are some rules and some tools that we can use to evaluate limits so that we can, if you're given a specific function, you will know how to find the limit of that function. Once we're able to do that, then we can use it as a stepping stone to get to some more work that we'll be doing later on. And so, this is, if you're in the text, this is section 1.3. And there are some properties. And now the notation that I'm going to use, is going to be a little bit different than what's in the text. The specific notation is not relevant. What matters is the basic idea. And that's what we're going to be after here. The first property is this. These are properties of limits. All limits possess these properties. Most of these, we are going to accept these properties as being correct without requiring a proof for it. There might be one or two where we could sort of hand wave through. I might do an extra video lesson that's optional to show you why these are true. But for most of our work, essentially for our work, we're going to assume that these are correct, these theorems are correct, and that we can use them then to find other limits. If most of you, I'm sure, are planning to become math majors, and when that happens, when you take your advanced calculus course, or if you go to graduate school, take an advanced calculus, you'll actually generate the proofs for all these. And so I want to leave something for that. So I'll leave the fun for later on. For us, we're going to accept these as being theorems without requiring a proof. The first is this: the limit as x goes to a of c. Let's assume c is a constant. So c is a real number, c is a constant value. The question is, what is the limit of a constant function? You have dealt with constant functions before, right? C might be, you might be 3, so you would have the constant function at 3. So we're talking about very simple, very basic kinds of functions. What if we have the limit of a constant? And it turns out that the limit of a constant is the constant. The limit of a constant is the constant. The limit of a constant is the constant. Eventually that just rolls off the tongue. The limit of a constant is the constant. The limit of a constant is the constant. And so let's do some specific cases. If we have the limit as x approaches, a can be any value. It doesn't matter what this is. A and c don't need to be the same number. They might. It doesn't matter what a is. It doesn't matter what c is. A could be 15, and the constant c might be 8. What is the limit of a constant? It doesn't matter what you're approaching. The limit of a constant is the constant. What's the limit as x approaches -2 of 193? The limit of a constant is the constant. What's the limit as x approaches -487 of the constant 8? That's 8. The limit of a constant is the constant. And so that's what this rule is saying. The limit of a constant is the constant. And c is, you're free to allow c to be any constant we wish. Second property. Limit as x approaches a of the function x. It's the identity function. It's the ordinary garden variety function that you've dealt with lots of times in a basic algebra course. Right? Here's the function. The limit as x approaches a of the function x. This is about as simple a function as you can get. It's equal to a. So let's do a specific case of that. Let's do a specific case. The limit as x approaches a is free to be anything you like it to be. Limit as x approaches 4 of the function x. And what is the rule? Essentially, all you do is you take this value, substitute it for x, and evaluate. Limit as x approaches 4 of x is equal to 4. The end. Limit as x approaches 20 of x is 20, because the rule is you take that value, substitute for the variable. Take that value, substitute for the variable. Take that value, substitute for the variable. So the limit as x approaches a of x is equal to the value of a. All right? So, what's our next little property? This one was the limit x approaches a of x is a. Third property, limit as x approaches a of x raised to the n. So n is allowed to be any natural number. All right? N is allowed to be any natural number. If x is, as limit as x goes to a of n, what if you have x raised to a power? Well, it turns out, and we could go through a proof of this, but we won't. It turns out what you need to have is a raised to the n power. And so it looks like that all you need to do for this is take this value of a and substitute it in for x. Because that's all we did here. Take a, substitute it in for x. We took a, well, there's no x to substitute, so just leave it alone. Take a, substitute it in for x. It turns out that's going to be a unifying theme through much of the work we're going to do. What are some specific cases of this? A specific case would be this. Limit as x approaches, a can be any number. Limit as x approaches 4 of x to the third is 4 to the third, which is 64. Limit as x approaches -1 of x to the 7th is -1 to the 7th, which is -1. Limit x approaches 10 of x to the 4th is, let's make that 10 to the 4th, which is 10,000. And so yes, in fact, that is in point of fact, that's the rule. It turns out the net effect is take a, substitute for x, work it out. Take a, substitute for x, work it out. Take a, substitute. If there is no x to substitute, then ignore it, and then the limit of a constant is the constant. Now, that's okay as far as it goes, but we have not addressed a few other questions. What about something like this? Notice there's not a plus sign in sight anywhere here. There's not a plus sign, there's not a multiplication sign anywhere. So what if we said this? What is the limit as x approaches, let's say 2 of, let's say, x to the third plus x to the 4th? Now we do have a plus sign. Well, if this weren't present, we would know what to do. If this weren't present, we would know what to do. The question is, they are both present. What do we do with that? And that's what the next set of properties is going to be on about. And so, again, in no particular order, and my notation might not match precisely what the text is using. I guess I'll restart my numbering. For example, I believe the text uses C. I tend to use A as the value that X is approaching. That's just a style thing. That it is not required that it has to be A or C or D or K or whatever letter you want to pick, but I just tend to choose A. It says this, K times the function. Now let's do, when we do these rules, let's make this a little bit more straightforward. So we know a few things. Let's back up the truck a little bit. Limit as X approaches 2 of X to the third. We know what that is, right? We know what that is. We know that's rule number 3 from our previous work. This is 2 to the third, right? This is 2 to the third power. That's 8. We know the limit as X approaches 2 of X to the fourth, right? We know that from our previous work. That's 2 to the fourth, which is 16. What we are asked is, what is the limit as X approaches 2 of X to the third plus X to the fourth? What does that equal to? Well, you might have a guess, and what we're going to do is establish the rule that says that's not a guess, it's an accurate computation. That's what we're going to be after here. And I'm going to leave rule number 1 alone for a minute. I'm going to talk about rule number 2 as it's listed in the text, the sequence. I'm going to talk about rule number 2 because rule number 2 goes to what we're talking about over here. All right? It says as X approaches A of f of X plus G of X. This now introduces, you'll notice the 3 rules we did at the very start, there were no plus signs. Now this is the rule that says, how do you handle it if you have 2 things added together? That's what this rule covers. We have a function plus a function. That is exactly what we're looking for. And it turns out the rule is this. The limit of the function, the sum, the limit of the sum, this is SUM, right? Limit of the sum, all you do is this. You take the limit of the first one, and you add to it the limit of the second one. The limit of 2 things added together is, remember how we said, if this were not present, we would know what to do. If this is not present, we would know what to do. But now they are both present. What you do is you take the limit of the first one as if the second one were not even present. And then you take the limit of the second one as if the first one were not even present. And when you find those results, just add them together. In my little example here, A is 2. Now, one rule is these must be the same number. If this is 2 and this is 3, this rule doesn't work. So they must have the same rule on all the values that X is approaching, the same value. X approaches A, X approaches A, X approaches A. If this is X goes to 2 and this is X goes to, let's say, 5, then these rules don't combine in this fashion. All right? But we do have they're approaching the same value. And so in our problem, in our little specific example, the role of A is being played by 2. Do we see that? The role of f of X is being played by X to the third. Do you see this is X approaches A. This is my f of X, which is X to the third. And this is my G of X, which is X to the fourth, right? And so what this rule says is, you evaluate the first as if the second were not here. We just did that out here. Then you evaluate the second as if the first were not present. We did that here. So the net effect is evaluate the first, which is 8, evaluate the second, which is 16, and when you get finished, add those 2 pieces together. and 8 and 16 are 24, I think. Now, the specific numbers are irrelevant. What matters is the general principle. The limit of two things add together is you find the limit of the first and the limit of the second, and then you add them together. The limit of two things added together is you find the limit of the first, you find the limit of the second, and then you add them together. Or, let me rewrite this from scratch and say it as I write it. The limit of the sum, S-U-M, the limit of the sum is the sum of the limits. The limit of the sum is the sum of the limits. And if you hang around the math course long enough, you're going to hear that kind of thing over and over and over and over again. The limit of the sum is the sum of the limits. When we get there, we will say the derivative of the sum is the sum of the derivatives. When we get there, we will say the integral of the sum is the sum of the integrals. So that kind of language occurs over and over again. You'll get used to it, and it's a convenient way to remember what's actually happening. Being able to write down the specific rule is not what's important. What is most important is you understand what's happening in terms of this computation. Because what this says is, now you can add together as many as you like, because there's nothing magic about adding two of them together. You can add 2 or 3 or 4 or 5. Any finite number of functions you can add together, and the limit of the sum is the sum of the limits. You can extend this. Technically, you would do that by math induction, but for our purposes, it suffices to say this is true of any sum, the sum of any functions here. The limit of the sum is the sum of the limits. And once we have that, then the next one is very easy. It works with plus. It also works with minus. Rather than write a brand new rule here, what I'm going to say is plus or minus. The limit of f of x plus or minus g of x is the limit of f plus or minus g of x. If it's plus, it's plus. If it's minus, it's minus. So even if this had been subtract, then this would have been subtract. This would have been subtract, and that would have been -8. All right? So, even though it's actually sum or difference, we typically just say sum. The limit of the sum is the sum of the limits. And so that talks about what happens if you add together functions. So now, from here on out, anytime we have functions added together, we know how to find the limits. You find the limit of the first and the second and the third and the fourth and add them or subtract them as is required. Now, let's go back to rule number 1. Rule number 1 says, what if you have a constant multiplier? See, we don't have any coefficients here. So rule number 1 talks about, let's consider this function. Let's see, what do we have? We had 2, we had x goes to 2, we had x to the 4th. That's 2 to the 4th, which was 16. So what if we had this? What if we had the limit as x approaches 2 of, what if we had 5 times x to the 3rd? That's what we have. See, k times a function, that's k times a function. So this property talks about what to do in this particular scenario. Well, it's not particularly challenging to show, and in fact, it is the case that this. What you need to do is, if you want the limit of 5 times some function, what you first do is find the limit of that function. And we know that's 8 already. So find the limit as usual, and then multiply by 5 when you finish. Find the limit, here's what that means. Find the limit as usual, and then multiply by 5. And see what happens essentially? Essentially, this constant multiplier, it's similar. It is not the same thing. It's similar to, some students want to say, don't you factor that out? Well, you're not factoring. It's a property of the limits. But yes, this constant multiplier, you may either multiply in here or you may multiply out front. You may find the limit of the product, and this is 5 times the limit of the expression. And so that's the specific case. How would that look here? In our case, in our problem, the role of k is being played by 5. And so we see how we would write this? The limit of k times the function is k times the limit of the function. And what we say is this constant multiplier just multiplies along. Constant multipliers multiply along. Constant multipliers multiply along. If this were an ordinary face-to-face class where I would have 30 people sitting in front of me in the classroom, then I would have, what happens is it's almost like students become my little minions. They're like my flying monkeys and I'm the wicked witch. I say, what do constant multipliers do? And all the students kind of say, multiply along. And I say, what is the limit of the sum? And all the students say, it's the sum of the limits. And so it's almost like this dark, it's like the dark side of the force or something. But the limit of the sum is the sum of the limits. Constant multipliers multiply along. We will find out when we do derivatives later on. Constant multipliers multiply along. When we do integrals, constant multipliers multiply along. So that principle is going to carry through various places in the coursework. Constant multipliers multiply along. The limit of the sum is the sum of the limits. And so this tells us, we now know, if I want to find the limit of x approaches 2 of, let's suppose we want to find 3 times x to the 4th. What does this say? You evaluate this as usual. Constant multipliers just multiply along. What is the value? This is 2 to the 4th. This is 2 to the 4th. This is 3 times 16, which is, what is that, 48? Constant multipliers multiply along. Constant multipliers multiply along. Third property. The limit of the sum is the sum of the limits. Now the next question is, and we'll kind of speed this up a little bit now, f of x times g of x. This is the limit of the product. And yes, it turns out the limit of the product is the product of the limits. Now, this is the official way to write it. The limit of f times g is the limit of f times the limit of g. That's the official way to write it. That's not the important piece. The important piece of the puzzle is that you know that the limit of the product is the product of the limits, that you know how to use it in practice. That's what's important. So the limit of two things multiplied is you multiply the limits. And if it works for add, if it works for subtract, if it works for multiply, it seems like it ought to work for divide. And it turns out it does. The limit of a fraction is you do the limit of the top, divide by, I'm going to run out of space here, the limit of the bottom. The limit of a fraction is the limit of the top divided by limit of bottom. The limit of the fraction is the fraction of the limits. The limit of the fraction is the fraction of the limits. Some people say quotient. Now, there's one requirement here. The requirement here, of course, is the denominator may not be 0. So if this assumes the limit as x approaches a of g of x is not equal to 0. So anytime you have a fraction expression, you always need to assume denominator is not 0. So constant multipliers multiply along. Limit of the sum is the sum of the limits. Limit of the difference. Limit of the product. Limit of the quotient. And there's one more. Let me go ahead and throw this up here. Our last one we're going to work with here is, let's do the radical of the function, limit of the radical. This is equal to the limit x approaches a of f of x. So the limit of the radical is a radical. First evaluate the limit and then do the radical. So if n, remember this, if n is 3, this is third root. If n is 2, this is square root. So let's assume n is 2. This is the square root. Then what this says is the limit of the square root is first do the limit, then do the square root. All right? Now, this is assuming this is defined. Remember, if this value is a negative number, then square roots of negatives don't work. Fourth roots of negatives don't work. So assuming things are defined, then this property still holds. Now, that's a lot of properties, and that's a lot of time, and that's a long video. But this is really the takeaway. From your side of the camera, what is the takeaway? From your side of the camera, here's the takeaway. To evaluate a limit, substitute and simplify. Now, in grad school, we called this plug and chug, but that's grad school. You might not want to do that. But substitute and simplify, plug and chug, if you will. So what does that mean? First off, if that works, if this works, you're done. If it doesn't, then we're going to develop some more rules and techniques to how to handle that. So if that works, you're done. So let's see what we have here. So let's do some specific cases. What is the limit as x approaches 2 of 3x to the fourth plus 2x to the third minus 7x minus 8? This is a polynomial. Look, we got things added or subtracted. We know what to do. We have constant multipliers. We know what to do. We have the limit of something raised x to the fourth power. We know what to do. We have the limit of a constant. We know what to do. So the net overall effect, when you combine all those properties together, the net effect is, what you do is you take 2, substitute it in for all the x's, and evaluate it. This is 2 to the fourth, plus 2 times 2 to the third, minus 7 times 2, minus 8, and that's whatever that is. That's 3 times 16 is 3 times 16 is 48. That's 2 to the third is 8. 2 times 8 is 16. 7 times 2 is a number. That's negative 14, and that's negative 8. And I'm guessing that is probably going to end up being a number of some sort. This is 64 minus, minus 22. That is 42. If my arithmetic is correct, that should be accurate. But that's the principle. To evaluate a limit, the first thing you try is substitute, simplify. If that gives you the result, you're done. If it doesn't, then you need to try something else. The net effect of all those is there's a large variety of functions you know. Any polynomial function, this will work. Any radical function that you've dealt with, this process will work, assuming things are defined. You can't take the square root of a negative number. Any fraction function works. So if g of x is given by x to the third, we don't want that. Let's do it this way. Let's do the limit, and let's keep it easy. X approaches 3 of x squared minus 2 over 4x plus 1. Well, what do? You substitute, simplify. If you get a result, you're out. Substitute, 3 goes in for all the x's. So this is 3 to the second minus 2 over 4 times 3 plus 1. And that is 9 minus 2 is 7. And that's 12 and 1 make 13. And 7/13 is a wonderful number. Any polynomial, any rational function, assuming the denominator is not 0, any radical function, assuming it's defined, the way to evaluate the limit is substitute, simplify.